Well, hello, everybody. Welcome to the second day of SharkFest. We have some great talks lined up today, and we also have a great keynote, and it's going to be presented by Vern Paxson and Robin Sommer. They're the people behind the Zeek Network Security Monitor, and they also co-founded a company called Corelight Security. And without further ado, I'm going to hand the talk over to Vern and Robin.
Great, thank you very much. Hopefully my slides are showing. Get a nod from Robin. Yeah, good. Delighted to be here. I think, and one of the points I'll touch on in the talk is that our communities haven't really overlapped as much as maybe they could, and I think there's a lot of potential there. And so I'm Vern Paxson. I'm a professor at UC Berkeley and chief scientist at Corelight. And also a lot of the work done here was done at the International Computer Science Institute that I'll be talking about. And I'll briefly introduce Robin when I hand it off to him about halfway through the talk. So I'm going to start with just some brief perspectives in history on network monitoring that won't take too long, but I'll convey where I'm coming from. And then I'm going to discuss Zeek, which is really about automating network analysis. And in the process, also touch on some reflections just about the communities around network analysis. Then I'll hand it off to Robin, who'll talk about automating protocol parsing. And I think this is the more sort of meaty technical part of the talk. And also I think has potentially interesting relevance for synergies between the Zeek community and Wireshark. Let me briefly reflect on Wireshark, and I should frame this as I'm essentially a noob. I mean, I use it, awesome tool, but I'm not at all a sophisticated user, and there may be lots of things about it I just don't know and don't appreciate. And so that may come through in my talk, and if so, I'd love to learn more about you know, how to leverage it. When I do reflect on it, I think, you know, this is the premier tool one uses to interactively explore networking activity. Just an awesome tool, and I use it in my classes and for detailed work, technical work as well. And really a wonderful example of a flourishing open source project, which is a theme I'll come back to because Zeek took a while to get there. And if I'm crawling through the source code correctly, roughly 1,600 protocol dissectors and 3 million lines of code, along with the stuff that's auto-generated, and hundreds of contributors. Really, really neat. And also, it's been around a long time. In particular, if you trust Wikipedia, in 1998, Wireshark appears at Ethereal at the time. So really, you know, decades of a vibrant project. So I find, bear with me a little, I'm going to illustrate a deep sort of tie here among the network analysis community. So who's not giving this talk? Well, it's not Steve McCann, who did Keynote at SharkFest back in 2011. And Steve did just fundamental stuff like libpcap and tcpdump, and of course, Riverbed, who's been fundamental, really, I think, to you know, SharkFest and keeping Wireshark vibrant. And, you know, like all of us, Steve was once a young guy. And there was also this amazingly dashing young guy way back in the day who actually is giving the talk. And the reason I make this tie is because, in fact, back in the 90s, Steve and I were buds. We were in the same office. We were both PhD students. And we were at Lawrence Berkeley Labs Network Research Group. And while Steve was doing this terrific stuff with libpcap and the like, I was leveraging it for this system called Bro. Also appearing in 1998, and that's when its public release was. And you may say, Bro, well, I thought you're talking about Zeek. Well, just as Ethereal became Wireshark, bro got renamed to Zeek. And I'm going to try to consistently use Zeek in this talk. There'll maybe be a few little bro snippets will sneak in, but for the most part, you know, it's Zeek today, and I'll just refer to it in the past as Zeek as well. Okay, so let me now talk about Zeek. And here I'm not a noob. I'm, you know, been doing it, working on it for, I started working on it 25 years ago. So a long time. I framed earlier how Wireshark's really the tool you go to for interactive network analysis. And I'll be bold enough to say, when you look at it, you just know what it does. The UI it immediately tells the story. Zeek is the premier tool for automating network analysis. And that's one of the key takeaways I'd like to have folks listening absorb, which is if you have a task that you're doing in Wireshark that you do repeatedly and kind of wish you could script it up more easily, Zeek may be the thing you want to use. However, it's got no UI at all, really. And that makes it hard for me to convey it. Like if I were doing a talk about Wireshark, I'd be just showing stuff out of the UI and it would convey it. But Zeek doesn't have that. So I'm going to instead try to give you the sense of what it does by talking about its architecture. To do that, let's first talk about Wireshark's architecture, and they have some similarities, and also get you sort of aligned with where I'm going for the Zeek part of this. So in Wireshark, you've got at the lower layer, capture of traffic. And you can capture live traffic and generally going to filter it down to what's interesting, the thing that you want to explore. Maybe though, you're instead reading it off of a trace file. And this all gets sucked into the core, and then the core is going to interact with the EPAN, which is where the protocol dissectors parse this stream of packets. And back comes from that a tree that the core is going to hand the UI to render. And not just render it, but allow interactivity. Hopefully I got that all right. That's my understanding, at least of the architecture. So what does this look like for Zeek? So I'm going to first sketch the architecture as Zeek was originally designed. That's a little simpler and gets to the heart of things. And then I'll show you how it's evolved, because it is now more involved and both in terms of richness and performance. So similar to Wireshark, at the lowest layer, there's, we're tapping the network and getting a copy of all the traffic. And then it gets filtered by libpcap. So here I get to use Steve's stuff, filter it down. And that in the original design was just vital. This system has a core design goal of being able to run at real time on a high volume link. And so at the time, it just couldn't do that if it looked at all the traffic. So it would strategically filter. The fact that this is libpcap also means that, like Wireshark, it can, of course, read trace files. And now this next part, so far, it looks just like Wireshark. This next part is different in some ways. That filtered stream goes into what we call the event engine. And a part here that is identical, really, to Wireshark in spirit is protocol parsing. So it has a bunch of dissectors that are going to pull out all the pieces of the messages. But then it goes a bit further, and it will turn those messages into events. And some of these events will even be distillations across multiple packets. For example, recovering the TCP byte stream, then parsing the HTTP, and then pulling out the headers. And each header might be an event, or will be an event if the user wants it. So I listed a few examples here. Hey, a connection was attempted, or I saw a reply from web request, and there was a file is the term for data items moved across the network. So for example, a data item returned in that web request. Hey, I wanted its hash, or you know what, it was a Windows PE, and here's the code. Those are all events. They have different semantic levels. Like that connection attempt is a layer 4 thing, and the HTTP replies a layer 7 thing, and the file stuff's essentially layer 8. There are a lot of these, currently about 650. And a key thing about the events in terms of security monitoring, which is the main use case, not the only use case for Zeek, is the events don't assume goodness or badness. They're just describing, hey, this is what's happening. Today, on a busy site, and now that event stream goes to a script interpreter. And hold on a sec, I'm getting a message here. Let me just double check. All right, we lost, I think, some audio, and hopefully it's back now. Yeah, okay. If I need to back up and explain something, just shoot it in the QA and I'll give that a go. All right, so I was explaining that the events, the processing of the events is done with scripts. And this is really the heart of the automation of Zeek. These scripts are written in a custom language, domain-specific language that's oriented around network analysis. It's a full Turing complete language. It's kind of like Python. You can think about a customized Python, and including rich data types and the like. And the scripts then process that event stream and do stuff. And here, conceptually, they do whatever you want to do. So what's your analysis task? And the scripts can have a whole bunch of state and consider other input sources and files with policy regarding a site, etc. They not only process, but they can react. And in particular, they can export logs. They can generate real-time alerts, various forms that can go into other systems that will process those alerts, and they can execute programs to respond. Those logs turned out, so in the original design, all of this was sort of meant to be equally important. The #1 use case today, though, is those logs. People run Zeek in order to have this detailed information about everything that happened in the past. Really valuable for analyzing incidents, investigating network weirdness, and threat hunting. And there's more than 60 types of logs that ship with the system. All in all, today, nearly 50,000 lines of scripts ship with the system. And that really is, I'm trying to convey, the heart of the system is leveraging this scripting. So that's the original design. Now, let me show how it's evolved to give you a flavor of what Zeek's like today. So this has turned into multiple instances of that architecture running using what we call Zeek cluster, which can spread processing across multiple distinct nodes or multiple cores within a multi-core system. So here, unlike Wireshark, Zeek has had to grapple with performance in a very challenging manner, which is how do you do this on these 500,000 event per second links without just dropping tons of traffic. And to do this, now we can't just tap the network generally, but we need either a packet broker that's going to spread it across multiple nodes or some sort of high performance NIC that can do spread it across the cores. There's no longer this this filtering, the static filtering, like, hey, I only want port 80 or whatever it was. And one of Zeek's nice features is that it can figure out what application protocols in use regardless of what port it's on. And it can do this efficiently. And essentially the way it does it is it just tries all its parsers and sees which ones work. And you would think that'd be too expensive, but there's some nice pre-filtering that can be done to actually make that quite inexpensive. So Zeek is blind to the port numbers and deciding what type of traffic it's seeing. But to do that, you can no longer statically filter in port numbers. On the other hand, Zeek also has a framework for dynamic filtering, which means that a script can decide, hey, you know, this flow is really high volume and I don't really care about it that much. So I would rather offload by not seeing any more packets from this particular flow. So it'll send down to the NIC the 5 tuple saying, don't bug me with that anymore. The types of events and the scripting have grown a great deal, and there's lots of libraries, hundreds of built-in functions alike in various frameworks. So it's a complex system, and I'll come back to that point in a minute. And similar to you know, a number of such projects, so we've migrated to a package facilities. So there's plugins, so one can dynamically add C++ code into the event engine, and scripts, of course. And currently there's about 150 of these. It's one of the core goals of the open source project to grow these. And I'm just gonna list a few very briefly so you get a flavor of how this system's used. Here's one that's looking at DNS and trying to find tunneling and command and control based on various properties of the requests. One that's looking for, hey, there's credit cards we're seeing in clear text. Those file names sure look like ransomware. Let's export into external framework. Let's decorate the logs with geo location information, computing hashes over SSH, crypto exchanges to fingerprint. And you can see also here, these all number of contributors, including, you know, Corelight, but also Brim, which is Steve McCann's current company, and Salesforce. Here's some more. This one is has essentially detonation style functionality where you grab an object and run it in a VM. Apache contributed one where we plug into Kafka. OS Query is a framework from Facebook where you can essentially an end agent, and so you can pull the agent information in the network analysis and so forth. Okay, so hopefully it gives you a sense of the system and how it can be used and its capabilities. Now, I want to briefly talk about the trajectory of the project. And boy, did it take a long time. So here is our amazing workshop in 2006. So this is 8 years after the first release of the project, public release. And that's the entire attendance of the workshop, about 8 people. And it grew very slowly, and mainly because, boy, it's complicated, right? I just showed you all these moving parts, and it took a long time to figure out how to make that more broadly accessible. It did, though, even from the get-go, for the gurus who did understand how to use it, make a really nice platform for research. And so it's been used extensively to pursue research in new ways of detecting attacks, new ways of network monitoring, refinements to such systems. And in particular, the National Science Foundation was vital to supporting this and just poured a lot of money into it. So this is quite different than most open source projects. Here is funding, and I don't mean to go through this in any detail, but I'm just trying to convey what it took to move this along. So the gray boxes, first off, each box, the length is how long the grant was for, and the overall area is the amount of funding. And so the gray is all the research stuff, and then the golden yellow is transition to practice funding, stuff to try to make it useful. And you can see in particular here, NSF put in almost $7 million into the project to try to make it viable for communities to use. And this is really the heart of what it took to get Zeek to a place where now we have, for example, Zeek Week and hundreds of attendees, just like SharkFest. NSF views this project as a huge success, and in particular, this is its budget request to Congress from in 2017, in which NSF said, these are the great things we did. For example, we hunted for gravity waves, and oh, by the way, we developed Zeek. So hugely valuable to have that support, and hugely appreciated by NSF. Zeek today is used all over the place. This is actually a slide from several years ago, and it was figuring out who's using Zeek based on either they talked about it in some, like at Zeek Week or whatever, or they have job positions looking for Zeek expertise, et cetera. So let me finish my part of this presentation reflecting on community. Our community, as I sketched at the beginning, it's old. You know, we've been around decades, and you know, there's a bunch of open source projects focused on network analysis in various ways that go back a long ways, and are widely used by practitioners all around the world. But you know, it's not really a community. It's more like communities. Namely, there's just not a lot of crosstalk like there could be, and this is why I was just thrilled to you know, get the invitation to talk here today. And just yesterday or sorry, 2 days ago at Zeek Week, we had the first time a presentation from the Suricata project. You know, just natural folks to be talking, and yet we don't tend to. And I think a lot of that is rooted in the fact that each of these projects kind of has its own language, and sometimes it's literally its own language, like with Zeek, and sometimes it is, you know, just the framework, the idioms, the knowledge base that goes into using the particular tools provided by the projects, and this makes it difficult to communicate. So I think, you know, it's a great question. Can we find synergies such that the projects work more effectively together? And I'm going to illustrate one and then hand things over to Robin. So one of these, which we developed as an effort at Corelight a couple of years ago and got a lot of traction, is a seemingly quite simple notion, which is, how do you get all these tools to refer to the same connection in the same way, so that if one of the tools has some sort of insight in that connection or data about that connection, one of the other tools can find it and link to it. And this isn't deeply hard, but it is, until Community ID was done, a pain because of how are things formatted and so forth. And Community ID essentially is a way of consistently hashing and then representing the hash of flow tuples. That's really all it is. And there are modules for various languages, and then you can see all of these tools now implemented so that they can use the same identifiers. And just last week, the Community ID support for Wireshark was been incorporated into the dev release. This is a blog by Christian Kreibich, who is the person who conceptualized and pushed along this project. So this is one example of how, as communities, we can bridge some of those, you know, different language, you know, conceptual language issues. All right, let me talk about other synergies. So there I am, this young guy in Berkeley, and not too long after that picture, along came this other young guy, and And this is Robin Sommer, who is about to talk with you. And in particular, so Robin goes back almost 20 years using Zeek. And 1 year after he started using it, he came to Berkeley, and we've worked together on it ever since, really, in various ways. And in 2010, Robin became the leader of the open source project. And so, sorry, stupid fly. This is the hazard of being outside. And in 2013, he and I and a couple others co-founded Correlate. So Robin is going to talk to you about a project that he's worked on for a long time in various forms, and it's called Spicy. And at this point, I will hand it over to Robin.
Thanks, Vern. Lots of photos of young folks here today. Let me share my screen real quick, just a sec. All right. I hope you guys can see this. Yeah, it's a pleasure to be speaking here. I'm with Vern there. It makes a lot of sense to try to bridge these communities. We're all working on very similar stuff. So thanks for the opportunity. I want to talk about a new project that we're just coming out with. And it's something which goes really to something that's at the core of Zeek. But it's also at the core of Wireshark, and it's actually at the core of Snore and Suricata, pretty much of any application looking at network traffic, and that is parsing protocols. On Wireshark terminology, I guess, dissecting protocols. I'm trying to use that terminology here. There we go. So one of the very first application dissecting protocols was arguably tcpdump. So what I did here is I'm just showing the tcpdump output on a tiny little TFTP trace that I borrowed from the Wireshark archive. TFTP is kind of, I guess, one of the most trivial real-world protocols you can think of. I mean, it's really just a file transfer over UDP, not reliable, just kind of requesting something by name, and then the data will come over. And you see, in terms of protocol dissection here, TCP doesn't show much for the data packets, but the very first packet there, there's a command code in there, you see a file name in there, and a transfer mode in there. And if you look at the RFC for TFTP, well, that's exactly those three fields that a read request has. So this is very simple, very basic a protocol. I kind of went to the source code of tcpdump to kind of look how this looks at that level, and you see it's pretty low level C code in the end. It's low level in the sense it's doing like point arithmetic. It's tracking length values. It's kind of mixing, I would say, the notion of parsing and presentation. So it's calling out into other functions, helper function that tcpdump offers, these print functions, which both kind of extract and display what's in there. This is kind of just for the read request roughly. If the whole file has about I think exactly 200 lines of code total in this style. And one thing, if you just look at this code, it's kind of hard, I would say, to see the simple structure of that original read request just by looking at this code. So it's very like low level. So I did the same for Wireshark. So Wireshark, looking at this tiny little trace, looks like this. In particular, that first packet there, you see the read request, you see the file names, the transfer type, and you see like down in the tree, the same is repeating. So this is the Wireshark code for parsing those fields. It's in the end not too different, I would say, structurally, right? I mean, also there are also raw pointers in there. There are size calculations in there. There's a bunch of helper functions. And it also kind of calls into the Wireshark engine, I would say, to kind of build up this tree as it parses that. So it's always kind of mixed and mingled. Turning to Zeek. So in Zeek, we actually don't, this is, by the way, it's 990 lines of code total for the TFTP analyzer in this Dissector. So analyzer is the Zeek terminology for this. So Dissector is the Wireshark terminology. On the Zeek side, we currently do not have a TFTP dissector. I'm going to add one in a few minutes, but until I get there, just for sake of comparison, how code looks like, I was looking at FTP here. So FTP, and when I was talking about this, I mean, the logs coming out of Zeek is essentially the immediate user interface, the results you're getting out of it. So in the FTP.log, if I put it onto a tiny little FTP trace, I see a few commands here with arguments. And this is being parsed out by code that looks like this. And this is C++ code now. Zeek is written in C++. And it's just for the originator side. And again, it's kind of piecing apart like a single line on that control session. And it's, again, not very different in the end. I mean, there are helper functions, there are raw pointers, there's pointer manipulation. It's again, if I look at this code, it's hard to actually see the structure of FTP in there. It's also calling out into Zeek code, like at the very bottom, is you see how these events are generated that Vern was talking about. The FTP analyzer in Zeek is 335 lines of code total, just for comparison. In the end, even if you have not written any dissectors yet, I mean, just by looking at this kind of code, it's probably pretty obvious that this is stuff that is, I mean, first, it's actually not fun to write. I mean, it's just so low level, and you have to be so careful. But it's also really, on a more fundamental level, hard. And there are three reasons why it's hard. And one is it actually has to be really robust. So if you're essentially, if you're dissecting network traffic, you're essentially working on untrusted input. So I mean, there's lots of stuff that does not conform to any RFC out there. You need to deal with that. From a security perspective, somebody might actually be actively trying to fool you and kind of try to crash your dissector, for example, by crafting traffic. So you just have to cover essentially all those corner cases in the traffic. Doing that in C, C++ is probably about the worst language you can find for that, of course. At the same time, and that's really unfortunate, the code needs to be really efficient, in particular for a real-time system like Zeek, where we sometimes in a large environment can have literally hundreds of thousands of concurrent connections. So Zeek's analyzers, they need to employ this very incremental stateful processing where they just jump back and forth between connections. They multiplex processing. When one packet comes in, it kind of, the analyzers just pass as far as they can, and then they move over back to other connections. They can never really buffer. Just because otherwise, with this volume, we would start dropping packets or running out of memory very soon. So this is something which is actually hard to write at a code level. So in addition to these other two, we also need actually to cover the whole stack of a protocol, right? I mean, so whatever we leave parts out, it's true for Wireshark, it's true for Zeek. That just means people can't see what's there, and that's not good. And unfortunately, protocols can be really, really complex, and that turns into a lot of work, and all that work needs to be robust and efficient. So given these challenges and the languages we are today writing this code in, it's in the end not too surprising that vulnerabilities in this space are essentially endemic. I mean, they are everywhere. And I took the liberty to look at the CVE history of Wireshark, and there are plenty vulnerabilities over the years in various categories. And without going in depth, I would venture to say that many of those are dissector related. Oops, sorry. Zeek is not any different. So we don't have that many formal CVEs. But for example, our current stable release is 3.0, and we maintained it for about a year, and we're getting close to the end of that. And over that time, we have pushed out 11 updates, and 8 of those 11 were fixing sometimes serious dissector issues. So it's the same, I think, in Suricata and Snort. Just one of the most common sources of vulnerabilities in this space. So that all leads to the question of how can we make it easier to develop robust and efficient dissectors? And to put that seed into your head, is there maybe even a way to benefit from what like the other communities in our space are doing? Can we maybe share some dissectors? And that is, if you remember the code I was showing, that is hard in the structure where like the dissecting that section logic and the application logic are so interweaved. So of course, people have thought about this before, and there are actually various projects have developed a variety of approaches to make it easier to write dissectors. And I'm not going into much of this, but I wanted to note that, I mean, it's interesting that both Wireshark and Suricata have started to add another language to the system that allows writing dissectors. So for Wireshark, it's Lua. For Suricata, it's Rust. And but what was good about this is basically that addresses the safety question, right? I mean, these languages are much safer to implement this kind of logic in than C or C++. At the same time, I would argue that these are domain independent languages in the end, right? There's nothing networking specific about it, nothing parsing specific about them. They're also still like essentially imperatives. I mean, if you look at the parsers written for Wireshark and Lingua or in Rust for Suricata, conceptually they don't look that different from this C code. It's safer, but it's the same kind of level of abstraction. It's still imperative in the sense you just describe step by step what's going to happen. A while ago already, I mean, this is like an earlier research effort that started, I think, 2005-ish, actually. We were looking at other domains and we're wondering if this is something to solve differently. And what's interesting is in programming languages, for programming language in particular, you'd see very robust tools that generate parsers actually from a different kind of input, namely from declarative specifications. And in yacc and Python, enter are the typical examples there. And what they take as input is a grammar consisting of productions that describe the language not too different from an RFC in the end, right? I mean, the left-hand side here is yacc's language for describing, or in this example, describing an expression, and it's pretty clear what's being parsed there. And then on the right-hand side, between the braces, in yacc's example, that is C code, then implementing the logic. So whenever there is an addition being parsed, I mean, you're going to execute that addition, right? And the C code expresses that. And this is very, very concise and lends itself very well to then being passed to yacc itself as a compiler generator that in the end will generate C code for you that you can just call and have, in this case, an expression parsed. Unfortunately, these parsers coming out of these tools are really not suitable for Zeek, which we were looking for at that time. And there are two main reasons for that. One is, I mean, just technically, the C code coming out of yacc, for example, is not able to do this highly concurrent incremental processing that I was talking about. And more generally, similar to Lua and Rust, yacc also does not have any domain-specific idioms built in. I mean, there's just no support for what we're needing. I mean, think about byte ordering, right? What maybe binary input by itself is a challenge for these tools. So we liked the idea. We didn't quite find what we needed, so we ended up writing something ourselves. And there was something came out in 2006, yacc for protocols called binpack, and it's essentially exactly that. It's a language similar to yacc, declarative, where you kind of just describe a protocol in terms of fields and types, and then have a parser generated for you. This example is actually taking out of the source code. It shows a TLS client hello message, and you can pretty directly see what's going on here. The part that is missing in this example, so you see the structure of the data unit that's being passed. Just like yacc, you now also need to add C++ code to actually glue it back into Zeek for generating events, because we need to do something with the data that we just passed. So binpack is actually the primary way these days how analyzers for Zeek are written. It solves a bunch of the problems in terms of the low-level parsing. However, I like to say it only solves half of the challenge in the end. So in that is, it remains limited to actually doing the parsing, the syntax part. But just as I was just saying, I mean, you still have to write that C++ logic for the integration. And that is first still very cumbersome. It's kind of the most uninteresting part about all of this. It also still leaves plenty of space for making further mistakes, and we have vulnerabilities in that area as well in the past. And the technical level, it's really just geared to application protocols. And it does not support some higher level domain-specific idioms that one would really like reassembly. A lot of protocols need reassembly of or defragmentation in one way or the other, and you end up writing that in C++ again, and it's hard. So with all that being said, so basically out of this experience with binback and writing Parsers by hand, of course, comes a new project that I'd like to present here. And that is, I call it Spicy, and it's the Spicy Parser generator. And the high-level point is that it's essentially a high-level scripting language for writing robust and efficient protocol dissectors. And that is meant in the sense of it's a closed system. So it uses this declarative syntax that we saw from yacc and we saw in binback. But it moves that additional part, the part between the braces, that what do we do with the data we just passed? It moves that into the language as well. And that's why it's really a scripting language. So you have like almost a little Python there with all the data types and normal mechanisms and some library support. So and the combination of this facilitates writing robust, stateful dissectors without a single line of C or C++. It has built-in support for a bunch of domain-specific stuff. I mean, the right types can deal with byte ordering. It has reassembly built in. Future versions will kind of figure out the protocol to be parsed in the first place. There's some errors recovery coming. It's really designed to facilitate composition and reuse, both inside a system. So if you can layer multiple spicy parsers, for example, to cover larger parts of the protocol stack, but you can also reuse external parsers by importing them, by extending them with additional logic, and then potentially still layering them. We're building this for Zeek, obviously, but it's designed in a way that it's really agnostic of the host application, in the sense that first it generates safe C++ code. I mean, so it's a parser generator, and it's C++ that's coming out of it. And that code has a pretty simple API for integration into applications. You hand in the data that you want to have parsed, and you have various ways of getting the results back. And then in addition, because there is of course application-specific stuff that needs to happen as stuff is being parsed, we employ glue generators for like that integration logic, and you have to write this glue generator essentially once per application. I'm going to show this. So let me show you an example. So back to the TFTP protocol, and that's the reason why I took this, because it's actually something that I can show end to end. So this is the spec. This is a little piece of spicy code for parsing a TFTP read request, and you define a type. You lay out the fields. It's a 2-byte opcode, and then it's 2 strings terminated by null bytes, and then at the end there's this line on done, and that is we call it a hook, and you see code between braces, and that is basically in this case it means whenever a read request has been fully parsed, then please execute this code, and in this case we're just printing it out, and that shows the values that have just been parsed. And this print itself is spicy language. As I said, there's no like going out to sea or anything. This is spicy language. I think I have actually maybe time to demonstrate this. Let me pull in a shell here. So what I have the same code that I was just showing in here in this file. I also have the UDP payload of this read request basically in a file. So because I only pass the application layer data, and I can take this and pipe it into a driver program that we have for Spicy, and I give this driver program the read request. So this takes a little bit, because what's happening is now the Spicy driver is taking the Spicy file, compiling it into C++ in the background, and then just in timing the code into memory and executing it, and then feeding it with that payload that I'm piping in. And what you're seeing is essentially I'll take this back. Yeah, oops, the wrong one. You're seeing the output of this print statement down here, right? That is why it's there, so that you see something being happening, and you see how the various fields have been parsed. So this is a closed system in that sense, that you can pipe this in. I have actually a full TFTP grammar in Spicy here. So this is a bit more complex because actually normally we wouldn't start with passing a request or a read request, because we first need to know what is the opcode, and then we need to dispatch based on the value of that opcode into different subtypes. And this is exactly what's happening here. So the entry point for the full TFTP parser is a packet. Opcode comes first. If it's this read request that we were looking at the whole time, then the switch will branch out into this one. It goes down into the request, and it will pass the file name and the mode right here. Right? And because read request and write request happen to be sharing the same structure, we implement that only once, and we pass a Boolean in so that we still retain that information, whether it's a read or a write. So, and there's actually, if I go down, this is all. Right? I mean, this is all that the original TFTP RFC describes. And if I look at this, this is about 33 lines. So I can take this and put the whole thing into TFTP. I'm going to use a different tool this time, because you probably noticed there was no print statement in there. Spicy dump is, it's kind of, as the name may suggest, it's meant as a tcpdump, a tool similar to tcpdump. In this case, it will automatically print the fields that we just passed. So again, it does this whole in the back just-in timing through C++, and then feeding the data in, and it prints out what it has just passed in a bit of a tree structure. So it just goes, iterates through all those fields. So this is essentially the spicy side of this. So you can write these parsers and you put them into code. You execute the code, you feed them. Let me go back to my slides for a second, real quick, because I want to switch to Zeek here. On the Zeek side, so we want to integrate this into Zeek. We do that. Zeek has a plugin API similar to Wireshark. So we are writing we added a spicy plugin to Zeek that, in the end, does something very similar to what I was showing in the standalone driver tool. It takes these spicy grammar files and compiles them either just in time, as I was showing, or you can actually also do it ahead of time, so to save that compilation time on execution. I was talking earlier about the glue that needs to be generated. So for Zeek, that primarily means we need to specify what kind of events in the model that Vern was describing, what kind of events do we want to generate out of those packets, out of those protocol elements, actually. And that we feed into the spicy plugin as well. And then finally, we, as always in Zeek, we put in like Zeek scripts that do something with these events. And I'm going back to my shell here to demonstrate that. So I still have the same full TFTP spicy here, right? That's the same file as before. The glue is described through a separate configuration file. And just really quick, basically it tells the spicy plugin that we are adding a protocol adding a protocol analyzer to, just a second, some technical issues here. Yeah, now we go. We're adding a protocol analyzer to Zeek. It's over UDP. This is the spicy unit we want to parse it with, and we want to pass everything on port 69 UDP with that. The more interesting part is this one here. So we say whenever we have passed one of these request units, and that was the one we are using for both reads and writes. And if that request unit is actually a read, then we want to generate an event on the Zeek side, and we want to pass on the file name and the mode that we just passed out. And the con is like a magic keyword that tells the Zeek plugin to provide information about which connection this is on. So I can take these two files and put them into a custom compiling tool, which is similar to Spicy Driver, except that it knows how to deal with a glue code on the Zeek side. And I can write that into a pre-compiled module this time. So basically, this is the more realistic way to use it. You would pre-compile your analyzer, save it, and essentially what's coming out of this is a shared library that the Zeek plugin is able to load later. And it's doing now both the compilation of the actual parser in TFTP spicy, and it's adding the glue code to generate these events and to kind of hook it into the Zeek pipeline. Takes a little bit, but once that is done, hopefully soon. There we go. Once that is done, I can start Zeek. And now I'm kind of feeding Zeek the full PCAP that have been looking at the whole time. I'm feeding it the HLTO file that we just compiled. And actually, I wasn't showing this yet. I have a tiny little Zeek script that just shows us something which handles this event. So just that we show that on the Zeek side in script land, it actually arrives. So we should be seeing this print statement here. Oops, I can do it this way. See, there we go. So this is the print statement coming out of that event handler. So we literally just added a full TFTP analyzer to Zeek, except that normally in script land on the script side, you would now do more and actually generate a log file, just as we saw earlier, the TFTP log file. But on the protocol analysis side, we added a full thing there. All right, that is the Zeek part. So this is generally giving us a nice capability now to really, or the ability, I would say, to lower the bar for writing these protocols, because you don't need C++. I also believe this is something that could be interesting to other applications in the space. And to make that point, we actually tried integrating this into Wireshark. And we wrote like a proof of concept, I would say, of a glue generator. And this is a command line. So the actual script, we wrote a script, make Wireshark plugin, that receives a spicy file, just like this TFTP spicy that I was just showing. Some more info about Wireshark, the installation, and where it should pass, just as you saw in the EVT file, and it outputs a Wireshark plugin. So I can start this. I don't have the time to go into detail here and, to show what it's doing, but I can demonstrate it. So I'm just going to run this with the very same TFTP spicy grammar that you guys already saw a few times now. So it does, like just on the Zeek side, it compiles that parser and then adds essentially some introspection logic to it that will interface it or integrate it into Wireshark. So there should be now my spicy SO here, right? So if I go back to this one, I have the command line here to get it into the Wireshark plugin directory. Oh, there was one there. And I can now open Wireshark and we'll see what happens. There we go. I have this trace here, and there we go. So this is Wireshark looking at this TFTP trace using the spicy dissector that we just added. And you see that in two things. The one you see like the info summary looks very similar, coincidentally, to those print statements that we had in our earlier TFTP code, right? And that's what it is, obviously. I mean, basically, this wrapper code at this point just prints the units into this line. And down here, you see the tree structure, similar to what tcpdump did. So it looks slightly different than what Wireshark would normally do. Let's make this a little bit nicer here on the right side with those print statements, because I'm going to quit it. We have a mechanism in TFTP that we can actually define how to string render one of these units that's being passed. And this is just code doing that. Basically, maybe you can see it down here for a request packet. So we render it very similar to what Wireshark standard by default would be doing for TFTP. So it means whenever something prints, please use this representation instead of like the default printing. And I've combined this TFTP Wireshark and the original Wireshark into a Wireshark all, just for technical reason, because our wrapper, our glue generator right now can only deal with one file. That is something that's to be fixed. And I can compile these together. And we're getting another plugin that now should be customizing how this output looks like. And this is actually, it's a simple example, but it shows how you can actually extend grammars that work generically, like the TFTP spicy is a generic grammar working for Zeek as well. But here we're extending it for Wireshark without touching it, so that we can actually make it nicer on the Wireshark side. So I'm copying that in there. I'm opening Wireshark again, same trace, and hopefully yes. So you see that basically we have now, this actually looks pretty much, I think, identical to how Wireshark TFTP looks by default. But you still see it's spicy by this tree structure down here, which you wouldn't have with a normal dissector. So this is one way to customize it. We could certainly extend this glue generator to do quite a few other things, like actually giving you control over the tree structure here in ways as you would normally have. By the way, one thing I didn't show is that the offsets actually are passed over as well. So you can see what has been passed. All right, that concludes the demo part. Actually, let's jump forward here a little bit because it's pretty much have the same on the slides. Yeah, so that brings me to the end of my part here. So I just want to say, so on the spicy side, so we are actively working on this, and there's plenty of ideas what we can do. So for example, we can certainly add more domain support. And one thing we have on our list is actually built-in ASN1 support of some kind. And I know Wireshark has its own tool for generating ASN1 code out of templates and specs. And this is something we could actually, on the spicy side, move into the language, I believe, if we find the right abstractions for that. We're working on error handling and recovery, which is particularly for Zeek, pretty important that if we're in the middle of a large HTTP session, for example, and we run into a trouble, we really like to synchronize at that next request so that we can continue dissecting that input stream. There's a pretty cool thing which we had in an earlier prototype that we could also reverse the whole process instead of dissecting, instead assembling new PCAP traces out of spicy. So that if you combine the two, then that gives us the capability for protocol-aware editing, like anonymization. We can first use spicy to dissect, we change the value of a field, and then we assemble again. And further applications domain file and log parsing. Actually, file parsing is something we're already doing on the Zeek side. So that brings me to my final slide, and that is the observation. So first, I mean, we're working to make this production ready for Zeek. So it's currently in beta. We're hoping for a stable release by end of the year, and we will just keep maintaining this as a core part of Zeek. That's the plan. We believe that this could be interesting to other projects too, and that, of course, is why we are presenting this here today. And as I already said, the Wireshark extension could be quite a bit extended, made nicer, made more dynamic, and generally, the thing is with these integrations is they really need to be just written once. And the moment you have them, basically, you have a much easier way to writing dissectors. There is, I think, the potential for spicy to enable actually our communities. And I would refer to Carter and Snort and others there as well to start sharing the sector. So at least the generic parts, the application independent parts, we could start sharing them. If you think about a protocol like SMB, it's just giant, SMB2, it's just giant. That would, I think, help everybody in the end. So, and we are very much interested in feedback on this. So this is some pointers to the repository there's a pretty extensive manual on how to use this all. On the Zeek Slack, we have a spicy channel. So whatever feels right for you providing feedback would be very much appreciated. And with that, I'm actually handing back to Vern at this point.
Great, thank you. I've got just one slide sort of wrapping up the talk. So we've tried to convey to you things about Zeek and spicy. And in particular, the real theme of this talk is let's leverage automation. Zeek is a great way to automate analyses that you might do repetitively or just want to codify so that you capture them and don't have to do them manually in the future, and also does it at high performance. Spicy automates generation of dissectors, which is, I think, really exciting in terms of both a lot less work, there's a lot simpler code, much smaller vulnerability surface, and finally, this opportunity to perhaps take communities and have a point of central community, singular, where we share the work of writing these things once and get them right and get them safe and performant. So with that, we are done, and happy to continue the dialogue in whatever form is appropriate. Back over to you, Gerald. Or Sherry.
Well, thank you, Vernon. Thank you, Robin. That was I thought it was an interesting presentation. Just you know, as from well, you know, I live inside, you know, Wireshark's internals from day to day, so that was a really cool presentation, I thought. And we do still have time for Q&A, and if you do have questions, you know, we of course still have the developer den open over in Discourse. So if you want to ask any questions about this, I'm you know, sure we could pick them up there as well. But looks like I don't see any open questions right now, so I think we can just maybe close the session out. But thank you two for coming. This is great.
Thanks very much for the opportunity. See you at Discord.
Yeah, thanks for having us. Thanks.
Thank you. Bye-bye.